Hey, Calc BC. Today we are covering lesson 7.9, the last lesson in our unit 7 on alternating series error. This is going to be a little bit a review of how alternating series error works, combining that with power series. And so we'll have X's involved. And then we'll also do a little bit of a review of Lagrange error bound as well. So we're in our last lesson in all of College Board's Unit 10, we've already covered the first half of their unit in our Unit 6, and now we are finishing up the last bit that we need to here. And we're going to be looking at error. All right, so let's switch over to the notes. All right, so here we go. Alternating series error. Everything up here is a review. I'm not going to read that to you. But hopefully those vocab terms make sense to you. Go ahead and read that if you need to as a reminder. This is what we're talking about here. For an alternating series, meaning meeting all three convergence hypotheses, so the terms have to be decreasing in magnitude, the limit has to be approaching 0, and the terms themselves have to be alternating in sign. The absolute value of the first term of the tail is an error bound. Okay, so alternating series remainder, we already know this. The absolute value of the first omitted or truncated term, a sub n plus 1, is greater than or equal to the error. So let's just take a look at example 1 and try this. Let's say we have a Taylor series about x equals 2 for a certain function f, and it converges to f of x for all x in some interval of convergence we're not given. The nth derivative of f at x equals 2 is given by f nth derivative of 2 equals -1 to the n over 3 to the n. So this is a little different than the normal way that we are given derivatives. This n actually represents which derivative we're on. So when n is 3, it means the third derivative at x equals 2 is this, with 3 plugged in for n. So that's kind of interesting. But let's see if we can apply this. So if we are going to write the second degree Taylor polynomial, we are going to need f of 2, f prime of 2, and f double prime of 2, right? And we're already given that f of 2 is 1/3. F prime of 2 means n is 1 in this equation. So we have -1 to the first over 3 to the first. So that's going to be -1/3. And the second derivative means we are plugging in 2 for n. So we're going to have -1 to the second over 3 to the second. So notice we're not plugging in 2 for each of these. The 2 is irrelevant to actually evaluating this fraction. It's all about which value or which level derivative we're on. So either first or second in this case. So this is going to become a +1 over 9. Okay, so now we can hopefully fairly easily write out our second degree Taylor polynomial. I'm going to do P2 of x. So we'll start with just 1/3. The second term will be -1/3 over 1 times x minus 2. And then we'll have 1/9 over 2 factorial times x minus 2 squared, which we could simplify to 1/3 minus 1/3 times x minus 2 plus 1/18 times x minus 2 squared. There we go. We answered letter A. Letter B, show that the second degree Taylor polynomial for f about x equals 2 approximates f of 3 with an error less than 0.01. All right, so question is this for certain, for sure, an alternating series? Let's check it. We need to know, are the terms alternating? Well, we've got this equation for the nth derivative, and sure enough, every single one is going to switch back and forth between positive and negative. So that's a check. Are the terms decreasing in magnitude? Well, every single time the denominator has this exponent in the variables in the exponent, so it's exponential. So it's going to be exponentially growing. So the denominator is going to be growing really fast, even though the first two are both 1/3. It's going to keep growing really fast, even though we have an x to a power that's technically in the numerator. An x squared grows way slower than 3 to a power. Um, and actually, you know what? I take that back because that's a difference between n and x. X is a constant. So it's this power that's growing. So this is going to be, let's see, 1, 2, 3, f is 3. Oh, we're plugging in 3 for x anyway. So 3 minus 2. The numerator is always going to be 1, no matter what that exponent is. So it's all about the denominator 3 to the n growing. So yeah, that's definitely increasing denominator, which means a decreasing fraction. And is the limit of the terms 0? That's also going to be a yes, because those fractions are going to keep decreasing, getting closer to 0. Okay, that's all we need to do there. We don't need to get too fancy with how much work I'm going to show. So that means that our error is going to be the third degree term, because it's the first omitted term. So we have absolute value of the third derivative at 2 over 3 factorial times x minus 2 to the third power. We want the whole term. Pretty similar actually to the Lagrange error bound, but we don't have to find some fancy pants capital M. We can just literally plug in the next derivative. So we're given this formula up here. I'll do this part over here. We have the third power of 2 is just going to be what? -1 to the third over 3 to the third, which will be what? -1 over 27. So back over here, this is going to be -1 over 27 over 3 factorial. We were told that x is 3, so it's going to be 3 minus 2 cubed, which really doesn't matter. So that goes away. We have 27 times 3 times 2. Absolute value is going to be 1 over 162. So we were supposed to show that that's less than 0.01. 0.01 is 1 over 100, so we're good. So 1 over 162 is our bound for our error, which is less than 1 over 100. So that's all we need to show. Okay, let's try example 2. Let f be a function with these derivatives when x is 2, and we have a graph of the fourth derivative between 2 and 3. So we could even label these x values 2 and 3. Blah, 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 blah. The graph is increasing from 2 to 3. Okay, find the third degree Taylor polynomial, p of x, about x equals 2 for the function f. We're already given all the derivatives that we need, so we can plug right in. I'm going to put the sub number 3 here so that we know exactly what we're doing. The first term is just going to be 4. Then we have -1/3 times x minus 2. We're centered at 2. Then we have -1/5. We needed 1 over 2 factorial times x minus 2 squared. I didn't really feel like writing a fraction in the numerator of this fraction, so I separated it and wrote the 1/5 first. It doesn't really matter. And then we have what? Plus 3/7 times 1 over 3 factorial times x minus 2 cubed. All right. I could simplify that if I wanted to. Sure, why not? We've got 4 minus 1/3 times x minus 2 minus 1/10 times x minus 2 squared plus 3's will cancel, so it's going to be 1 over 14 x minus 2 cubed. There's part A. Part B, use your answer to estimate the value of f of 2.8. So we know that f of 2.8 can be approximated by p sub 3, the third degree Taylor polynomial, at 2.8. If I plug that into a calculator, plugging in 2.8 for every x, which I already did previously, what I'm going to get is 3.705904762. I'm not chopping any of those values off because they might be necessary for part C. Part C, use the information from the graph to show that the error in our approximation is less than 1/8. Okay, so this lesson was focused on alternating series, but first of all, we're only given the first 3 derivatives. We are not told that the rest of the derivatives are going to be alternating. And even the ones that we have go positive, negative, negative, positive. And once we plug in, they're still that same way, positive, negative, negative, positive. These terms are not alternating. So since this is not alternating, we're going to have to use Lagrange error. So let's write that out. This is not alternating. Therefore, we must use Lagrange error bound. Okay, so let's see what we've got. We've got the third degree Taylor polynomial. So we're going to have to do the third remainder, which is going to have to be less than or equal to some m over 4 factorial times x minus 2, because we're centered at 2, to the 4th. So whatever term we stopped at, we always add 1 for the factorial and for the power over here. C is still where we're centered. We're going to be plugging in something for x. I can see already it's going to be 2.8. So we need to know what m is. And so let's try that out. I'm gonna write this out in words to see if this helps. M is the maximum y value on the 4th derivative of f between x and c. That's the definition of capital M. We want to get as close to that maximum as we can. And in this question, we know what x and what c are. C is, again, where we're centered. All the way back in the beginning, we were told that we're centered at 2. X is the number that we're currently plugging in for x. And you can tell right here, it's 2.8. It's the same that we did in part B. So we're looking for the maximum y value or some sort of upper bound on the y value of this 4th derivative between x and c, between 2 and 2.8. And lucky for us, we have a graph. Here is a graph of the 4th derivative. It looks like this. We're told that it's increasing from 2 to 3. And we are interested in the maximum y value between x and c, between 2 and 2.8. So 2.8 is going to be right around here probably. And so you can tell since this is increasing, right there is going to be our m. But I have no idea what that is. So we're just going to have to use 7. We know that it's less than 7. So 7 is going to have to be our m. It's the best we can do. It's the best we can do for an upper bound for this y value. Okay, so we're going to have to use 7. So and now we could say that remainder and the x that we're plugging in is 2.8. So I'm going to plug in 2.8 for x. And we're plugging in 7 for m and 2.8 for x. Okay, so I'm going to type that into my calculator, and when I do that, I get approximately 0.119. And so therefore, the error in our approximation is less than or equal to 0.119, which is indeed less than 1/8, which is what we were asked to show in the question. So it worked. So if you can prove that your series is in fact alternating and you have a way of finding the actual value of the next derivative, you can use alternating series error. Otherwise, you're going to have to use Lagrange error. And that M, again, is the trickiest part there. So hopefully that makes sense. Please let me know if you have any questions. And I hope you have a great day. Thanks for watching.